guys for being here and spending a week of your summer learning about elliptic curves and modular forms. I hope you have a great time, learn some stuff. Okay? My basic assumption about you is that someone at some point is the mic on? You guys are here. Okay, just in my head. My basic assumption about you is that somebody at some point has said the word modular form to you. You nodded agreeably, and maybe you read a little bit about it, but that's all. Okay, so if you haven't, and no one ever has, other than me just telling you the word modular form now, you might get more out of the competing course. I don't know which room it's in, where there'll be a nice, gentle introduction. But I think I'll review everything mostly that we need. Okay. If you are an expert in modular forms, you're going to be super bored. This course is not geared to you. You may want to find something else to read. Okay, so it's not for experts. For that reason, the goal is to be very explicit and computational with modular forms. So the basic arc of the course will be, we want to play with the upper half plane, draw geodesics, look at homology, draw loops, be very explicit combinatorial number theoretic so that you'll get to know and love modular curves, modular forms like they were your own. That has both the theoretical and computational algorithmic applications to it. So that's the general gist. There will be a link posted, but I'll write it here too. In case you have your laptops out and want to follow along. Wow, it's going to go pretty far. /J for late. Quant-book.pdf. Okay, is that still, that's kind of in the shadow though. Is that okay? Still? All right. Sorry, the whiteboard real estate is pretty valuable. This link I just posted last night, there's a document. I am in the middle of writing a book on quaternion algebras. That book is sadly not done. I don't know if it's ever going to be done. It's now 700 pages long. I apologize for the length, but there is a lot of supplementary reading and exercises in this book. Okay? Now, because it's a work in progress, if you do decide to read this and you see something that's wrong, or it doesn't really make any sense, you're confused about it, the explanation is unclear, or there's some magical step that you don't understand, I really would appreciate hearing about it. Okay, so you can come up and talk to me, you can send me an email as you like. I really appreciate that amount of feedback. It is sort of geared towards people like you beginning, trying to learn about the world of quaternion algebras, generally speaking. Later there will also be lectures on quaternion algebra, so it does really contain reading relevant to all the lectures, not just this one. But it has the upper half plane, Gauss-Bonnet, a bunch of exercises there, classical modular forms, SL2Z, that kind of stuff. So if you haven't, well, if you've seen that stuff before but want a little refresh, you want to practice around with it, or if I say something that you want to read more about, that's where the reading is. So I don't know exactly how the rest of the day is going to be structured with, there seem to be a lot of exercises and optionality, but one of the things I hope that we'll do is to work through some of those examples, okay? That's my contribution to that conversation. Are there any questions up till now, administratively or otherwise? Maybe we should just get started because time is already running out. Okay. Let's set up some basic notation. So upper half plane. So this is going to be my H. It's actually sometimes written H2. I don't know how sophisticated your font is, Fractory or \mathcal. Okay, but this is any way that you denote it. These are the points z equals x plus iy in the complex numbers, where the imaginary part of z which is y, is greater than 0. Okay, so I'll put a picture of the upper half plane up here. It's this part. Okay, so this set has a natural metric on it. The metric is ds. I'll tell you what the ds squared is. It looks like the usual metric on Euclidean space, dx squared, dy squared, but it's scaled by y. Okay? So similarly, this gives a an induced area metric in the usual way, like this. Now, do you guys know what this means when I write down metric? So if you want to, it gives the same topology on the upper half plane. If you think about, if 2 points are close, what does that mean, right? That's topology, what it usually says. It says that they're close if they're close to the usual sense of the picture, of how you're used to in the Euclidean sense. But the distance between 2 points is different. If you want to find the distance between 2 points, you have to find among all paths in the upper half plane between those 2 points, the one such that the integral of this thing, so I wrote ds squared and then I still wrote the square root. The integral of the square root of this thing, let me have to put a y squared
The
here.
y should be squared too.
Yeah, okay. Thank you. The integral of the square root of this thing, which now had the original, is minimized. That's what it means to have a path between. So what do the geodesics in the upper half plane look like? Well, if I were to take 2 points that have the same real part, what's the, I just drew, what's the shortest path between those 2 points? You guys seen some of this before?
Mm-hmm.
Okay, good, then tell me what the, I'm an interactive guy here. It's a big room, but vertical line is correct. It's a geodesic. What happens if they do not, I guess I have multicolors, as promised over here. So if I have 2 other points, what's the, how do I make a path between those?
Orthogonal to the wheels.
Correct. So I assume you ask that there be a form of right angle. So that's what it looks like. I picture the upper half plane like a skate park. If you imagine skating here, it slopes up coming at you as you try to hit the real axis. So it becomes very expensive for you to be traveling around in the skate park if you're very close to the real axis, which is why in order to get from here to here, you kind of skate downward to follow the groove, and then it brings you back up again. Okay, that's how I visualize that. The upper half plane, as a result of this calculation, it is a uniquely geodesic space. Bless you. Okay, so among all metric spaces, this is one that has, between any 2 points, there's a unique shortest path, one that minimizes the integral of the ds. The geodesics are vertical lines and semicircles. After you make such a, well, this is called a geometry, you would ask then about maps that preserve the metric on the space. So if this were just Euclidean geometry, this would be translations, rotations, reflections, and you must have studied those at some point. Similarly here, we have the orientation preserving isometry group. So this is called isom plus. Plus is for the orientation preserving. Here's your H. And it is PSL2R. This group acts on H by linear fractional transformations. So I have a matrix ABCD in PSL2R, and I have a point in the upper half plane. It acts as AZ plus B over CZ plus D. This is well defined because if I change the sign of my matrix by swapping the sign on all of A, B, C, and D, then I get the same number here. SL2R, you guys know these are the matrices of determinant 1 in, okay, I'll write that too. As you see, I like to be complete. Okay. The upper half plane, because of the skate park, you can try to skate to infinity and leave the upper half plane. You won't ever leave because it gets really hot. It just gets steeper and steeper as you head to the real axis. But you can still talk about the limit points achieved that way. So that would be what's called the thing I just erased here, the line at infinity. But there's also a point that wraps around, so you can also try to escape up in the question already.
Oh, could you move the monitor down? It's kind of hard to see.
Oh, absolutely, yeah. Does that work? That just changes it to somebody else's monitor. This does not actually go down. You know, we make our classrooms with all this tech and advancement, and then you end up with whiteboards and a screen and another one that clocks in. I think that's the best I can do. Is that all right? I'll try not to write in the corner. How about that? You guys can still see it in the back, Mike? Is it all right? Okay. There is the circle at infinity. So this is the boundary of the upper half plane in the usual sense of, I don't know, you think about it as a subset of a complex plane. This is the real axis together with the point at infinity inside C union infinity. One nice way to think about this is that if you flattened and you wrote your complex numbers as a plane sitting horizontally instead of vertically, so then your real axis sits like this, you can do so the upper half plane would be here. There's a stereographic projection. So the pointed, so now you're supposed to, and it intersects the, boy, that, I hope your picture's better than mine. It intersects the flat plane here along the circle, and this is the point of infinity. You guys have seen stereographic projection in some complex analysis class that gives you a bijection between C and the sphere minus infinity. So then now you are supposed to visibly see along the sphere is the real axis and the point at infinity. Okay. The PSL2R acts as well on this boundary. Same definition by just axing now AZ plus B over CZ plus B. If I plug in a real number or infinity, I will get a real number or infinity. And so linear fraction transformations. And we look at the completed upper half plane. Usually that's called H star, where you take H and you throw in the boundary. Okay, and this thing has a topology on it. I don't know how seriously the topology will figure, but if you're going to make a set and the original thing had a topology, you want to know what it means to be, at least to be close. Metric won't make any sense because we said it takes infinite, the distance to get to the boundary of infinity that's infinity. But if you hear what it looks like to take neighborhoods, if you want to take a neighborhood of infinity, what you do is you take all points with the imaginary part greater than or equal to some constant m. So this would be a neighborhood of infinity. You might think about that right now. If in stereographic projection, what does such a neighborhood look like? It looks like a neighborhood of infinity on the sphere. And if you take a point along the real axis, what does a neighborhood look like there? Well, the right way to think about it is there's a linear fractional transformation that will swap out infinity with your favorite point on the real axis. So it should just be taking whatever those neighborhoods were and considering what the image is under that linear fractional transformation. You guys know about Mobius transformations. They take circles and lines, circles and lines. Okay, so if the circle is going to, so the thing you end up getting looks like this. So it's supposed to be an open circle, a disk. But then it also needs to include that pointed along the real axis. So that's what the basis of neighborhoods of a point along the real axis is. Okay, the question so far? We are interested in subgroups of this big orientation preserving group, which is actually transitively on the upper half plane. So today we're going to spend some time talking about the group gamma, which is the group PSL2Z. So here you make the same definition, but you replace R with Z. This is a subgroup of PSL2R. What do you guys know about gamma, about PSL2Z? It's a discrete subgroup. Why is it discrete? That's just something you heard on the street? It's discrete because, yeah.
The integers are discrete.
Because the integers are discrete. You can think about this as, forget about the plus or minus 1, so lift back up to SL2Z. So what are these matrices? inside there, that's like, if we just considered all of M2 of Z, that would be like the integer sitting inside the real numbers, just 4 coordinates at a time. So I can't visualize 4-dimensional space, but you can. And if we restrict to saying, oh, I only want to look at the subset of matrices of determinant 1, well, still discrete. Okay, it's just sitting inside some weird 3-dimensional thing inside a 4-dimensional string, and we're looking at the lattice point inside. So it's a nice discrete group. What else do you know about this gamma? There's an obligatory picture coming of the fundamental domain, which those who know work in this domain, we have a way of recognizing each other on the street. We go like this, right? So you know that you're a modular forms practitioner. Okay, so we're getting there. How do you make that? You look for generators of this group. What are there's a nice set of generators, right? They're called
S and T.
S and T. What are S and T?
S equals 0, 1, negative 1, 0, or 0, negative 1, 1, 0. I don't know.
Does it matter?
What do you believe?
Inside PSL2Z, it doesn't matter.
And T is 1, 1, 0. Sorry, 1, 1, 0, 1.
And how do these act on the upper half plane? Well, this is going to send you to what wants to be reflection in the unit sphere, but because it's determinant 1, it can't be a reflection, so it makes up for it by sticking in a negative sign. And this one is the translation. Okay. We'll also need the matrix ST, which you can multiply out. It's this one. Okay. Visibly, if I do S twice, I get the identity. I can't write this lower, can I? Is that okay? Right? And this one you also have to check. ST cubed equals 1. I do not recommend multiplying out the matrix 3 times. I suggest you look at its characteristic polynomial. When I write equality, everything's always happening inside PSL2R. When you square this matrix, you get negative the identity, which is 1 as the identity inside the group. All right, here comes your picture. A short version of this course is everything you know and love about SL2Z, we should be able to do for all other finite index subgroups of SL2Z. Okay, and then maybe for all sorts of other discrete subgroups of PSL2R. Okay, so that's, if you know, that's why I'm reviewing this, so that you feel you know and love this object already. All right, here comes your picture. Okay, so you asked for a fundamental set for the action of this group gamma. Fundamental set, what does that mean? Well, we'd like to understand the action of the group. In order to do that, we should pick out representatives of the gamma orbits in the upper half plane. And a nice way to do that is to take the points that are closest to a given point here. Let me write down what the definition of a fundamental set is first. Sorry that they're the ghost of all of the previous things left up there, but the definition of fundamental set. Okay, so I'm going to try to make this happen. I don't know if it will, but there's my symbol for fundamental set. It is \Lazy lozenge. You run out of letters pretty quickly in this trade. F is bad, H is already used, S is bad. Trust me, this is you cannot confuse this symbol. It doesn't make for such a great lozenge because of the, you actually swallow this and you kind of jaggy in your throat, but it is a good picture of what the fundamental domain looks like too. So it's really quite, I highly recommend, I'm going to make this happen. So if you have a group gamma and you want to know a fundamental set for the group gamma, well, first of all, I want some basic topological properties. If I take the interior of the set, I take the closure of the set, I want to get the set back. So don't try to do something crazy like sprinkle a bunch of points, random discrete set of points randomly over the upper half plane. That's not going to help you. Second of all, I want if I take the gamma images of the set, I want it to cover all of H. Number 1 in particular implies that my fundamental sets are closed. Number 3, I want no 2 interiors to intersect. Well, I'll write gamma here, slightly better. So if I take not equal to the identity, okay, so if I take Lazy and I take gamma Lazy, so translate of it under the group, look at the interiors of those, I want that to be empty, And lastly, I don't want you to try to do something weird on the boundary with some bizarre space-filling curve or something stupid like that. So I ask that the area of the boundary is 0. So this is the hyperbolic area. Okay, this is a subset of the upper half plane. It makes sense to ask about the area of that set. I want it to be area of 0. Okay? That's what it means to be a fundamental set. So this picture here is supposed to be a fundamental set for the upper half plane. How is it described? Well, this is the unit circle. Believably so? No. Okay, hope your picture's better.
It's the unit parabola.
It's the unit. I told you it's a skate park, right? So I'm trying to warp it for your. Okay. And if you want, so this is the fundamental set. You might ask about what do the translates of this set look like, and you hopefully have seen a picture like that before, but if not, here it is. This is what you get if you apply S way Z. Here's what you would get if you apply T way Z. And similarly, you would have all sorts of copies over here. They continue on here. This would be the T inverse. And around here, there are more copies too. What else do I want to say here? This, maybe I should give you the definition of this set. That would probably help. So this is the set of Z, the property that the absolute value of the real part is less than or equal to a half, and the absolute value of Z is greater than or equal to 1. Okay, so I took the intersection of things with absolute value greater or equal to 1, real part between minus a half and a half. That gives me this set here. Okay, so this thing is a fundamental set. Okay, most of the time people say domain here instead of set. You decide. For me, if you satisfy the first 3, you're a fundamental set, and if you satisfy the 4th, then you're a fundamental domain. The domain being that I have to be, this extra condition requires more than just a topology. I need a notion of volume or area, so that gives you a little more flexibility if you have a group action. Let's see, what else are we going to do with this set here? What happens when you glue together according to the gluing relations implied by the group gamma? So this is in the video game metric, when you're flying around in the quotient here, whenever you try to leave, you end up back on the other side by the identification of Z goes to Z plus 1. What happens if you fly down into here? Well, you pop back up again on this side, because of the Z goes to minus 1 over Z. So in the quotient, well, it kind of looks like this. It's a little bit funny because you can try to escape to infinity. This shrinks to a point that's missing, which is infinity. And if you glue, well, there's like corners here and here. So these corners will be identified, so you get a little bit more. It looks sort of more like this area here. When you glue together this edge and this edge, you get something which is called a cone point. And around here, because you're identifying this edge, well, it sort of loops around to be, you don't have a full 2 pi neighborhood, you only have a pi neighborhood here. So there are points here that are called I, and I call it rho or omega. Strictly speaking, it's probably better to put your omega here and I here so you're not reflecting it. So this is like one of those corn chips. That's my attempt to make it a little three-dimensional. So it's a surface, right, that you glue together that way, but it's an infinite corn chip. But it has finite area, okay, very salty. So the theorem is that this set here is fundamental domain gamma equals ds of 2z. S and T generate gamma, and and there's a reduction algorithm. Okay, so if you haven't seen any of this before, I'll explain all of the details to you in the book. This reduction algorithm, what does it mean to have a reduction algorithm? It says that if I took any 2 by 2 matrix with determinant 1 integer entry, so an element of SL2Z, there's an algorithm that will write it in terms of these generators, S and T. Okay, because just because I told you that they generate, that might not help you. Somebody gave you a matrix and said, prove to me that this matrix belongs to upper half plane, okay? That belongs to these, that these actually generate. So that's part of what comes out of the proof of this theorem, is that you can see how to write it as a word. And you guys have seen that before too, some of you maybe. Okay, when you stare at this theorem, this is where we're headed, for, like I said, for the rest of the week. What happens if I replace PSL2Z with another finite index subgroup? We want some kind of really explicit description of the probably saltier corn chip. What do the generators look like, etc. Okay, so that's why we're want to make sure everyone's at least seen one example before. You guys, this reduction algorithm comes in many forms. It also gives you reduction for binary quadratic forms, so in some sense it goes back to Gauss. Let's do an example. The explicit guide's better than trying to describe the algorithm in steps or something. So here is a 2 by 2 matrix. Its determinant is 3 minus 2 equals 1. Prove to me that this belongs to the group generated by S and T. Well, here's the proof. We're going to use the picture. One of the great things about working with these kinds of, whenever somebody gives you a group, it's hard to visualize a group like that. It's a discrete group, so it looks like a set of points. So we visualize the group by its action on the upper half plane. Okay, so we're going to understand this element by what it does to points in the upper half plane. Okay, so let's take the point 2i. I'm not going to take I or rho because they're stable. They're elements that stabilize these points. S stabilizes this guy, and ST stabilizes this point here. Okay, so if I take 2i, well, I can just hit it with gamma. Okay, and it's going to land somewhere. Where does it go? Okay, well, gamma z0, that's acting by linear fractional transformations. This is going to be, okay, I can do this, 6i plus 1 over 4i plus 1. You can too. All right, now I have to ask robots to help simplify. Maybe you don't need that kind of help, but I'm getting old. Here's what happens when you multiply top and bottom by the conjugate of the denominator. Okay, so you get some point. All right, so there's your z1. So what do we do with the z1? Well, we'd like to move it back to the fundamental domain. That's what this allows us to, so the duality between the picture and the generator. How do we move to the fundamental domain? Well, first of all, I guess I should at least ensure that the real part is between minus a half and a half. I can accomplish that by translation. What should I that will translate by an integer. How much should I translate this guy by? 1. Gonna subtract just a 1. Okay? So we'll call this guy z1. The z2 will be t inverse z1. That just subtracts 1, which will give me 8 over 8 plus 2i over 17. Now what? Okay, so now it lives somewhere between these two ballasts. I would be done if its absolute value was bigger than 1. Is that absolute value bigger than 1? The answer is, check for yourself, no. Too small. The imaginary part is too small, right? Okay, so what do? Well, we reflect with the s. If I'm taking something like z goes to minus 1 over z, that's like I said, it's like reflection but also negation, so it's orientation preserving. That increases the imaginary part. Okay, so we absolute value of z2 squared is 4 over 17. The z3 we reflect. Okay, and then you keep repeating. So the next step would be to translate again. What should I translate by? Add 2. So my z4 is going to be t squared z cubed. Sorry, z3, excuse me. And the thing that will come out of that is now called I over 2. Is that a coincidence? No, one more step, right? z5 is the s z4. That's going to be the 2i. Okay, so I managed to start at 2i, and then I move somewhere, then I move back. What am I doing? Well, I'm either translating or reflecting, and because I understand what that's happening with the t or the s, equivalently I am moving along the tessellation, the upper half plane, in a way that always brings me back to the upper. So what does that mean? Well, if you write this all out, I really should have had breakfast. Corn chip was looking tasty. This is the thing that we just decided. Times z0 is equal to z0, right? Okay, but you check that the stabilizer of this z0, which is 2i in gamma, is equal to 1. I mean, we picked, that's why I picked it to be that point. So it's not a vertex or a point with non-trivial stabilizer. Okay, well that means that this is actually, so gamma equals st squared, st inverse inverse. S is its own inverse. Okay? That's it. Check. Question?
Yes, okay, so for the reduction algorithm, our goal is to write this arbitrary element of gamma in terms of S and T. That's all
That's
we're
it.
doing.
That's
Okay.
it. Feel good about that? Very explicit. You could write a little computer program, 5 lines or something. Okay, yeah. So it's very, okay, awesome. So now what we'd like to do is to replace SL2Z with another finite index subgroup and do all of that. Okay, so it's a remarkably rich theory. So I hope this was, you felt really good about. I wanted to just start on Monday morning feeling really connected to the material. It will get increasingly abstract, but I want to have all of this for those other subgroups. Okay? So our favorite any other questions before I proceed with that? Okay, so our favorite subgroups are the congruent subgroups, but they are the only ones that we care about. And actually much of what I'll do today works perfectly fine for non-congruent subgroups, but let's focus on the money, where the money is.